Okay, so now that we know about pressure in a gas, we can start to understand why balloons can float up into the air, and why objects can float in fluids. Right. So first, just to draw a quick picture, earlier we had talked about having, say, a gas inside some container. All of the particles of this gas were flying every which way, bouncing into the walls of the container, and since they exerted a force on the container equal and opposite to the force the container exerted on them to reverse, to change their momentum, there was average forces from all these gas particles flying around on the walls of their container. But the gas particles wouldn't just bump into the walls of the container. If we imagined putting something inside of this box, say, we put a sphere inside, gas particles would also start kind of bouncing off of this sphere inside. So they would bounce off the walls, they would bounce off something inside as well. Okay, and so whenever we have an object immersed in a fluid, whether that is having an object inside the gas, inside a room filled with gas, or inside a lake filled with water, the particles in that fluid are constantly hitting the surface of the object, exerting a pressure. There's an average amount of force distributed over the surface area of that object, right? And sometimes the total forces involved in all of those collisions cancel out, right? So if you just have a ball sitting on the ground, the collisions of the particles don't spontaneously make the ball lift up on its own. But the forces involved can actually be reasonably large. And so if there's an imbalance in how the forces are distributed over the surface of an object, you can get interesting effects, as we'll see in this section. Okay. So in fact, if it weren't for gravity, all of the forces from, say, the collisions between the gas particles and this sphere sitting inside of the gas would tend to cancel out. The pressure inside a stationary fluid would be uniform everywhere. Okay. But because of gravity, in fact, there is a gradient of pressure. So I'm going to say there's a gradient of pressure due to gravity. Okay. Maybe you've experienced this while swimming underwater. For instance, if you dive to the bottom of a pool, it feels like there's more pressure on you than if you're floating just below the surface, right? And so, in fact, as you go down in a fluid, the pressure tends to increase, right? And so what that means is if we're, looking at this sphere and it's, immersed in a gas in Earth's atmosphere, say, so it's immersed in the air and there's gravity, so gravity is present. And if you look at, what are all of the, random forces from all these collisions between gas particles and the sphere, well, actually, those forces tend to be a little bit bigger on the bottom than they are on the top. Right? And so the fluid below an object, because of gravity, will have a higher pressure than the fluid above the object. And if you kind of average all of those forces together, there's a net upward force due to this pressure imbalance. And that's what we call buoyancy, or the buoyant force. Okay? And let's start out by thinking, how big is this buoyant force? What is its magnitude? Is it big enough to lift something up or not, right? And to start thinking about this, let's start out with a little thought experiment. Okay, so let's imagine, we're standing on a platform, I guess, and we're gonna hold, there's some water, so I guess, there we go, we're on the ground, and what we're gonna do is hold a bag filled with water by a string. Okay, I'm going to say this bag is really, it's just some thin plastic substance. We've got some rope attached to it. And let's suppose that this bag is, let's say the bag has a volume of 1 cubic meter, right? I don't really care what the shape of it is because the bag is just some floppy thing. But it's got about a cubic meter of volume inside of it. And what we've done is actually filled it completely with water. Okay, so there's no air bubbles, there's nothing like that. totally filled up. And then we're dunking it underwater, okay? One question that we have is, how much force do I need to exert on the rope in order to keep this bag in place underwater, okay? So let me make some space here because I need to draw some diagrams. Let's say bag has 1 cubic meter of volume, and I'm going to say it's filled with water. Okay, well, what forces are acting on this bag in the first place? Water has mass, so gravity is acting on it, and if I use the kind of standard numbers for like what is about the density of water, what is the acceleration due to gravity, there is a weight pulling down on this bag, right, due to gravity, which turns out to be about 9,777 newtons, okay? That comes from, water is a little bit less than 1,000 kilograms per cubic meter multiplied by the acceleration due to gravity. Okay, so I know at the very least that this force is pulling down on the bag filled with water. The question that I have, though, in this thought experiment is how much force do I need to exert on the rope in order to keep the bag in place? And in fact, the answer is none. Like, I don't need to supply any other force to keep this bag at whatever level it is, right? Just as if you have a pool full of still water, the water is not experiencing any net forces that are kind of constantly generating, oh, this blob of water is sinking and then reflowing out and something like that. There's no net force that I need to supply in order to keep this bag floating where it is, right? What that tells me is that there is a buoyant force, and I'm drawing it off-center just so it doesn't get in the way of my illustration. In this case, there's a buoyant force, which must be exactly canceling the weight of the bag full of water in the first place. So this is 9,777 newtons, right? And somehow that total buoyant force has to be coming from this kind of effect. The pressure of the water hitting the bag is a little bit bigger below the bag than it is above the bag, okay? And that imbalance leads to a net upward force when this bag is immersed in a pool full of water or something, okay? So lots and lots of tiny collisions summing up to this level of force, okay? And so apparently, in this case, we've figured out that the buoyant force is supporting exactly the weight of this bag full of water, right? So just as the water itself, if I were to take the bag away, wouldn't be experiencing any net forces suspended in other water, this bag is just going to float neutrally at whatever depth we lower it to, okay? And that's reflected in the fact that the buoyant force exactly balances the weight, the force due to gravity, and so the bag doesn't experience any net accelerations. Okay. I want to kind of continue thinking about this thought experiment, but now suppose I have, and now I'm just going to start drawing objects as squares because it's just a little bit easy to draw. Suppose I have something which is twice as dense as water, okay? So I still have 1 meter cubed of some substance, but I say that, the density is twice as much, so same volume, twice as dense. That means the weight of the object, the force of gravity pulling down, is going to be twice as big, right? So that's going to be 19,554 newtons. Okay. It still occupies 1 cubic meter of space. What's going to happen when I lower it into the pool? Well, it's not like the water molecules in the pool know what's inside the container they're bumping against. Right here, they're bumping against some whatever flimsy plastic bag full of something. Here, they're bumping against the same flimsy plastic bag filled with something else. The water molecules don't know anything about that. And so in fact, they exert exactly these same kind of, average forces over the surface. There's still exactly the same imbalance in the bigger pressure below versus the smaller pressure above. So the buoyant force here is exactly the same as it was when this bag was filled with water, right? So here the buoyant force is again 9,777 newtons. And so that means that there is a net downward force, F net on this thing from the weight and the force of buoyancy, which is, 9,777 newtons, right? Twice that going down minus that amount going up equals this amount pointing down. So if we wanted to keep this bag of denser material at the same height, then we would need to supply an additional force, right? Okay, let's think about the same reasoning, but what if this object was twice as voluminous, right? So it's going to be the same substance, but now, let's suppose there's something that has the same mass, but is occupying twice as much volume, right? So I'm going to say it's the same mass, so it's yet another substance occupying 2 cubic meters of space. And so, well, if it's the same mass, the weight is the same, m times g. So I'm asserting, in this case, it's still this. Now we're actually back to something that has the same mass as 2 cubic meters of water. So apparently the buoyant force here, I know water is going to sit neutrally wherever I put it. So I've got a different substance. Maybe it's not like the water molecule's outside. No, I've got a different substance. It's got the same mass as 2 cubic meters of water. And so the buoyant force is going to be exactly enough to balance out that downward weight, 19,554 newtons. Okay. So again, we have something that wouldn't require any additional force of us holding up a rope or anything. This thing will experience no net accelerations. Okay. As a third example, and now I'm not going to redraw the whole thing. I'm just going to, do something like this. Suppose we had an object with the same mass, so I'm filling it with yet another substance, so that the weight is 19,554 newtons. But now I say that there's 3 cubic meters of space. Okay. Well, by the same chain of reasoning, I could say the buoyant force on this, must be the same force that would balance out 3 cubic meters if it was water. So the buoyant force here, F buoyant, must be 3 times this number. So that's, like 29,331 newtons. Okay, and so here there's a net upward force. Okay, and that means that this thing isn't just going to float at this height. It's going to experience an upward acceleration, until it's eventually, right? So you might say like it's experiencing a net upward force of 977 newtons, and so it's going to rise up. When it gets to the top surface, it's going to keep rising until the forces on it are balanced, right? And so it's going to float a little bit above the surface, right? And we can figure out how far above the surface is it going to float, because the mass of the object has not changed, right? So the downward force is still 19,554 newtons, and it's going to rise until there's no net force on it anymore, right? It will then no longer experience any accelerations. So I know that the net force acting up on this has to be, at the end of this process, 19,554 newtons. And what that tells me is that it must be the case that underneath, the surface of the water is 2 cubic meters of the stuff, and above the surface of the water is 1 cubic meter of this, bag of stuff, or whatever this object is, right? Because 2 cubic meters of something underwater is the amount of object underwater that would lead to this much of an upward buoyant force acting on the object. Okay. Okay. So what we've actually just discovered is called Archimedes' principle. Archimedes' principle. Which is the idea that if you have an object which is totally submerged in a fluid or partially submerged in a fluid, immersed object in a fluid will experience a net. Will experience not necessarily a net, but will experience an upward buoyant force, which is equal to the weight of the volume of fluid that object displaces. So upward buoyant force equal to the weight of the fluid displaced by that object. Okay. Such an object will be experiencing at least 2 forces. There'll be a downward force due to gravity acting on the mass of the object itself, and there'll be an upward buoyant force related to the volume of fluid that the object is displacing. Right? So for instance here, our one bag of 1 cubic meter bag of water was displacing 1 cubic meter of water, and it experienced an upward buoyant force equal to the weight of 1 cubic meter of water, right? And so that's why these numbers exactly canceled. Here we had a different object. Its weight was whatever it is, but its volume was a cubic meter, so it was displacing a cubic meter of water. So there was an upward buoyant force of the weight of 1 cubic meter of water. So on and so forth through all of these other examples that we kind of walked through. Okay, so this already tells us that an object will float or sink in air or in water or in any other fluid as a function of the balance between these two net forces, right? So if an object is displacing a volume of fluid and the weight of that volume of fluid is greater than the weight of the object itself, the object will float. And if it doesn't, it will sink. Okay. So I guess fun historical interlude. Archimedes, famous Greek philosopher, educator, so on and so forth, was the subject of the famous Eureka Epiphany. He's the person who shouted Eureka, and the context of him discovering this principle was that he had been asked by some random king whether a crown was made out of gold or not, or if the crown had secretly been debased by mixing some gold and some silver together, right? And so the trick here was that it's easy enough to know, well, at the time, Archimedes level technology, it was easy enough to figure out the weight of the crown, right? They had scales, and so they could figure out the weight. And they knew the densities of, silver and of gold. But how do you figure out the volume of a complicated shape? If the crown was just a cube, they could weigh it, they could measure the volume really easily, and then know if it was pure gold or gold mixed with something else. But if you've got something that's a weird shape, how do you figure this out? The legend goes that while Archimedes was taking a bath, he saw the bath water rise in the tub as he got in, and he realized that the amount of water, that rose up, or if the bathtub had been totally full, the amount of water that would spill over had to be exactly his own volume. He was displacing his own volume of fluid, and so if he could submerge the crown in a totally full tub, the spillover would be the volume of the crown. You could measure the volume of the water more easily by putting it in a regular shaped container and then figuring out if the crown was gold or silver. This was apparently so exciting that Archimedes then ran naked through the streets of Syracuse shouting Eureka, which in Greek means I've found it. And that's why we still have that saying today, I suppose. Great. So there we go. We've answered this question. What is the magnitude of the buoyant force when we immerse an object in a fluid, right? And again, the big idea is that because of gravity, there's an imbalance, there's a gradient in the pressure as you go through a fluid. So the pressure below an object, because of gravity, is going to be greater than the pressure above an object. And when you average that pressure imbalance over the surface area of the object itself, you get a net upward buoyant force. Okay, so when will things float? When will things float? So for instance, why can a steel boat float in water, even though steel itself has a greater density than water does? It's because, a boat has a shape. So if I look at like a cross-sectional view, this is kind of like what the hull of a boat looks like. It tends to float kind of like this. The boat is not solid steel. It's like a steel shell, and then there's, decks and people on them and stuff. I don't know. I'm not a boat person. There's a sail. Well, I don't know. Whatever. Doesn't matter. It's a boat. So, when the boat is like this, it's displacing not very much water. As it goes deeper and deeper, and the water line where the water meets the boat's hull rises, the boat is displacing more and more volume of water until the volume of water displaced is equal to the weight of the boat itself, right? So it's the shape of the boat. Why can a helium balloon float in air? A helium balloon, so here's a balloon filled with helium. A helium balloon can float in air because the mass of helium is less than the mass of the air. So if you fill a helium balloon to the same pressure as the surrounding air, the total mass of the helium atoms inside will be less than the equivalent mass of the air particles that it would have taken to fill the balloon up to the same pressure, right? So one helium atom is only like 10 or 15% the weight of an average air particle, okay? So that's why kind of things like boats and helium balloons float. It's because they have a net upward buoyant force, which is big enough to counteract their own weight. Okay. What about hot air balloons? What about hot air balloons? Which are not filled with helium, but just with, hot air. What's going on there? So, a helium balloon, we've got maybe this, there's like a burner and a basket. There we go. Great. I guess we need to draw something on the balloon itself to make it a little happier. There we go. Air only has a density, which is about, air density is only, about 1.2-ish kilograms per meter cubed at sea level, right? And, because of that, not many things actually float naturally in it, right? Most objects have a density most materials have a density which is bigger than the density of air, and so the amount of air they displace is not enough to make them lift up, right? So how can we get, like a balloon to float? One thing that we could do would be to fill a bag with a lighter substance, say a lighter substance like helium, right? The other thing that we can do is fill the bag with a less dense version of the same substance, right? And that's what's going on here. So, what we need to do first is to make sure the balloon of the hot air balloon stays inflated. And in order to do that, we need to make sure that there's as much pressure, acting from the inside of the balloon, pushing the envelope of the balloon out, as there is, pressure pushing the envelope of the balloon in, just due to, the outside air. So when you've got a balloon, say you've filled a balloon with something and tied it off, air pressure is trying to push the balloon in, and pressure from the gas inside the balloon is trying to push the envelope of the balloon out until there's a balance between those two pressures, right? So what we want to do is somehow fill this balloon with a less dense version of air, but that has the same pressure as the air outside of it, right? And the ideal gas law that we saw earlier in this class points us to exactly how to do that. Right, so earlier we saw that the pressure that a gas was exerting was equal to Boltzmann's constant times, let's say, the density of the substance multiplied by the temperature. So one way that we can, get the upward buoyant force acting on this balloon to be bigger than the weight of the balloon itself is to fill it with air, which is at a lower density. So, the trick here, try to fill it with air that's at a lower density so that there's a net upward force due to buoyancy, which is bigger than the balloon's own weight. And to make the pressure balance so that the balloon stays inflated, we do that by simultaneously increasing the temperature. So we fill the balloon up, not with a different substance like helium, but with a hotter, lower density version of the same substance. There's fewer particles inside the balloon, but they're moving faster, so they have the same pressure acting out against the balloon as the atmosphere does acting in on the balloon. And the reason hot air balloons need to be so big is that, you can't make this temperature humongous before the balloon itself experiences problems and, you're standing some distance from this burner, you don't want to be roasted. So you can only make the difference in density inside the hot air balloon versus the outside air. You can only make that difference in density so big. And so you need a huge volume of this less dense air in order to lift up like a person.